Thank you very much, Farshad, for joining us and I guess giving up your time to present to the NGen today. So as I mentioned earlier, Farshad is actually one of our own committee members and the D2 liaison, which covers the area of is it telecommunication and information technologies. Is that right, Farshad?
Yep. Yeah. IT and communication technologies. Yep.
So very, very lucky, I guess, to have a committee that's getting involved and being involved in presenting and sharing their knowledge. But a little bit to Farshad's background. So Farshad completed his bachelor's degree with honours in electrical engineering, which majored in telecommunications at the University of Kazvin in Iran in 2012. During this time, he actually spent some time working as an employee of a mobile carrier in Iran as well. After completing his undergraduate degree, Farshad migrated to Australia, where he completed a master's degree in telecommunications, as well as a master's degree in engineering project management, both of which were at the University of Melbourne. In 2016, Farshad began work at TasNetworks as a graduate telecommunications engineer. During this period, he worked across several teams, including telecommunications customer engineering, service delivery, telecommunications, network operations, and continuous business improvement. In 2017, Farshad completed a secondment acting as Senior Telecommunications Engineer in the Customer Engineering and Delivery team, and in 2018, he was permanently appointed to this role. Throughout his career, Farshad has designed and delivered fibre optic solutions to many government and private enterprises, either as a part of their own infrastructure or within TasNetworks data centres. Farshad also, as a part of his role, analyses and manages the geolocation of telecommunication assets with the aim of identifying strategic business opportunities and delivering commercial services. So Farshad, again, once again, thank you very much for giving up your time. I will hand it over to you from here on out. So we'll just go through the process of setting you up to share your slides, which should be good to go.
Yes. All right, excellent.
All right, the floor is yours. I can see that perfectly, and I will go on to mute now and just sit in the background, mate.
Fantastic, thank you. Good afternoon, everyone, and thank you, Matthew, for your great bio, and you perfectly pronounced my name. My name is Farshad Charmchi. I'll just correct something that Matthew mentioned. My current role is actually a telecommunication engineer, not a senior. Today's presentation, basically, we are going to cover overview of telecommunication network. So as Matthew mentioned, I'm a telecommunication engineer at TasNetworks, and TasNetworks is a power transmitter and distributor in Tasmania. So the main purpose and role of TasNetworks is to transmit and provide power to residential and commercial basically users in Tasmania. To make that possible, also TasNetworks required a level of telecommunication network for protection and control of their assets. As a result of it, over time, they have developed and installed a number of hilltop towers and underground or overhead fiber optic cables to be able to protect their sites. By evolving the technology and having this network around this space, TasNetworks also decided to use that network not only for the purpose of operating their network, but also to use it for commercial purposes. So in today's presentation, I'm gonna talk about the foundation of this telecommunication network, how this telecommunication network, not just TasNetworks telecommunication network, any type of telecommunication network, how it is designed, and we will just take it slightly to the advanced level of what are the factors and features required to operate a telecommunication network. So by having that in mind, I will go through the agenda quickly. So as I said, first we will talk about a little bit about all different types of transmission mediums. I apologize in advance if some of these topics may be a bit basics, but based on my experience and having experience with my peers in electrical engines in the rest of the business, I every now and then find that they ask a question in some of these areas and topics. So I decided to cover all the bases and foundations before we even start going through the advanced. So maybe in future we have another session with a bit more advanced topics, but for today we will just stick with a bit of a foundation. After the transmission mediums, we will go through a bit more into depths of one of the transmission mediums, which is the fiber optic cable, widely used around the globe, and it is basically the foundation of the telecommunication of the internet and all the telecommunication networks. After that, we'll move on to a bit of concepts of how the data is transferred, the TCP/IP model, and some of the tools, some of the structures that we use to transmit to increase the transmission rate by using WDM, SDH, PTH, and Ethernet type of network. So you may have heard these types of networks, but I'm just going to explain it a bit more and show them how they're sitting in the TCP/IP with basic analogies. So it will basically fit together and make more sense to you by the end of the session, hopefully. After that, we will talk a little bit about data centers and points of presence and communication facilities and how these sort of infrastructure fit into the whole puzzle, why we require those sort of infrastructures. And to close it off at the end, I will talk a little bit about TasNetworks and 4224 telecommunication network, why we have 4224, what happened because of the regulator. We decided to go from TasNetwork model to 4224 structure. Excellent. So every time that I think about this whole communication network, the simplest way to talk about the telecommunication network is basically to compare it with normal communication that we make on day-to-day basis talking to our friends. So imagine the situation, you're sitting in a room with your friend. It is a fairly busy room and you're trying to convey a message to your friend, you're trying to make a conversation with your friend. So the first thing happens is that the message that you are thinking about in your brain, it will be encoded. That encoded message, it will go to your, it will become a neural signal, so we'll convert it to neural signals, and the neural signals will basically go through multiple organs into your lungs, into your vocal folds and vocal strings, your mouth, your tongue. And what happens is that as you push the air out, it will vibrate the vocal folds and the vocal strings. It will vibrate the noise and create a vibration on the air. The vibrated air travels through the air, hits your friend's receiver, which is in this case ears, and it will go through the ear canals and eardrum, hit the eardrum. The eardrum will convert that waves into neural signals again. Neural signals go into the brain, and the message will be decoded in your friend's brain to understand what you're trying to say. Now, there are a few features and factors that are here that are important to convey the message. The first of all is the noise in the room. If the room is too noisy, well, there is a good chance that you cannot actually fully convey your message. If you guys are far away from each other with your friends, then again, the volume of your voice, the power of your voice might be too low and it might not be fully conveyed to your friend. There are certain protocols that are involved here. If you are not speaking the same language as a protocol, then your friend will not understand what you're saying and basically drop all the input data, all the input packets, and it will just basically ignore it. So as you can see, there are lots of sort of structures used here that we sort of use them in the same method, obviously in the machine language into analog and digital language to be able to communicate to between the equipment, between our switches and routers and those sort of machines we have got between our computers. So the first thing we need to focus on is the transmission medium. So in this case, it was the air that was vibrating and going from the mouth to the ear. Similar to that, in the telecommunication industry, we have got multiple transmission mediums. So in general, we can break the transmission mediums into two categories: guided medias and unguided medias. The guided medias is when, as the name suggests, there is a guide, there is a cable, there is a pipe that you can control and send the signal over that pipe. The unguided media is basically where you can communicate over the open space without any cable or pipes. So let's have a quick look at each of these and see what are the pros and cons of each of these equipment, each of these transmission mediums. So the first one is the twisted pair cable. So twisted pair cables is I'm pretty sure you all have seen it. You use it for your Ethernet network on your laptops. Used to be in some of the houses, if there is still having the landline, it is connected, or the DSL modems were connected to the landlines via these twisted pair cables. It is made out of at least two copper cables twisted to each other, wide or twisted to each other. So I'm pretty sure you all know if the current flows through a conductor, it will create electromagnetic radiations. If you have got these currents are going through opposite directions, the electromagnetic radiation will be created in opposite directions, and when you twist them together, they will basically cancel each other out. In the twisted pair cable, we have got at least a pair, but normally for your LAN cables, you have got up to 4 pairs. 2 pairs are responsible for transmitting, 2 pairs are responsible for receiving. Twisted pair cable is really easy to use. It is, and as I said, is widely used in your house internet connection. If you're connecting to your modem to your computer with a instead of Wi-Fi with the Ethernet cable, you're using that cable. It is relatively cheap. The only downside of it, or there are a few downsides with it, is twisted pair cable acts really good in short distance, but in the long distance, it will really quickly drop the bandwidth. So if you're one of the unlucky people and having a NBN connection that is a FTTC or FTTN, which basically a fiber to the cabinet or a node, you all know and experience that your bandwidth might not be as good as someone who has a fiber directly coming to the premises, to their house. And the reason for that is the way that the NBN is structured is basically the fiber cable is going to a cabinet. It could be on the street, in your street or the next street. And then from there is a copper cable coming to your house. If that copper cable, the length of that copper cable goes beyond 100 meters, 200 meters, then your bandwidth is gonna drop really quickly. So it is good, it is cheap, it is easy to use. However, it has a certain limit in terms of the length. Also, the other issue of it is a bit of a security issue. So twisted pair cables, if you're a fan of Mission Impossible movies, you have always noticed they walk into a data center, put a listener on Cat6 cables, and they can tap into the feeders of cameras and see what is happening, or they can corrupt the whole network. So basically, it is not as simple as what they showed in the movie, but realistically, yes, because there is still there can be a certain level of electromagnetic radiation. What will happen is that if you have got the right equipment, you will be able to, without the network owner knowing it, you will be able to listen to what they're actually doing in their network. So after the twisted pair cable, there is another type of cables that you all have seen it before. It is the coaxial cable. Coaxial cable is used in your houses to connect a TV antenna into your TV. It has again 2 conductors. The main conductor at the center of it, it's located at the center, and then you have got the insulated, the between insulated with the plastic, and then you have got another conductor on the outer shield of it. So what happens here, again, same scenario, the electromagnetic field will be completely cancel each other out. It has a better immunity to interference, this cable, and it has a better bandwidth. As a result of it, especially in North America, it has been used for broadband networks. So many of the cable TVs, what they used to have was the service providers, they would provide between two different frequencies. They used to provide the media for TVs, and also they used to provide the broadband on a different frequency. So the ISP was providing both of them in separate sort of frequencies. The issue with them is, again, length is not the best friend. So in long distances, they're going to lose their bandwidth. And also, given the size of them, if you use them to deliver connection into multiple houses or to the multiple equipment, then it is not going to be very cost effective or easy to install because they can be bulky. The third of the guided media, the third media on the guided media is the optical fiber cable. And as I mentioned before, we are going to go more in depth of the fiber optic cable. But for now, we are just going to explain a little bit about how the fiber optic cable works. Basically, the fiber optic cable is created out of a strand of very tiny strand of glass, or these days it's also made out of plastic. With a high density, surrounded by a lower density glass or plastic. And how it works basically is that based on the Snell's law, it says that if you are sending a signal, a light signal, through a media, isotropic media, and it hits the boundary in a certain degree, a certain angle, then the light can have different scenarios. It can completely go through, or it can refract, or it can reflect back within the media. So the way that they have designed the fiber optic cable is that they've made sure that because of the density of these two medias, the inner fiberglass, which is a very, very pure glass, and the outer cladding, as they call it, the shield, that is less pure glass. They have chosen these two ratios in a way that in certain angles when you transmit light, the light will be completely trapped inside and it wouldn't go out or refract out off to the second media. As I said, again, I will go more in depth of how it looks like and all different types of it, but that's how it works. As all we know, the speed of light in vacuum is 300,000 kilometers per second. Obviously, this is not vacuum, but you can, and there are certain factors involved: what type of cable, what length of the cable you're analyzing, the diameter of the cable. All of the factors are important, but generally speaking, the speed of light in a fiber optic cable is about 70% of the speed of light in a vacuum. So it is roughly sitting around 200,000 kilometers per second. So it's fairly fast. And because of that, we will go through it and I will show you a photo of it, that it is widely used around the globe, under the seas, on countries, between the cities, to transmit data, because the data can be transmitted really, really fast. On the unguided media section, we have got the radio waves. Radio waves are basically multicasting waves. So the best example of them is the AM and FM radio. So the frequency, the function is between 3 kilohertz to about 1 gigahertz, and they have got a really good penetration factor, so they can actually penetrate through glass or a bit of concrete they can penetrate into, so then you can easily listen to your radio inside of a house. After the issue with the radio waves is basically it is out there, everyone can have access into it, so the security of it is not amazing. And you can create certain channels to listen into the radio waves, and there are ways of making it secure, but the actual media is not as secure as, for example, the fiber optic cable. The second type of unguided media is a microwave links. Microwave links, is part of the radio waves. They are not multicasting, so basically they are they work based on a direct path, or they will need to have a direct line of sight between the antennas and dishes to function. So when an engineer designs these towers, they will need to consider a lot of factors to make sure that the direct path is achieved. But also, it is not just about the actual direct factor or the signal that is sent from the transmitter. It can be reflected on multiple paths, and it will still be received by this receiver with a bit of a delay. So it is important to design your network considering the regional atmosphere and factors in that region, to design your network and to decide what should be the height of the towers, and where should the should be the size of the antennas, to be able to minimize all of these side effects of it, and maximize your basically bandwidth and your link reliability. The issue with these, first I will say the value of these links is that they're really good. They're useful for long distances, especially if you want to connect into a remote area. So many of the power stations and substations, they are located in remote areas. Connecting them with the fiber optic cable might not be possible. So as a result of it, having a radio tower on top of a hill, sending a signal to that remote area would be the most sort of the best possible solution to provide comms to the site. However, the downside of it is, first of all, the cost, the installation cost of the towers, the antennas. It has a high sort of capital cost to start it. But also there is a ongoing operational cost involved with this sort of asset that you need to maintain, not just the tower and the antenna, but also the access path to the site. These sites, generally speaking, are on top of the hills because they need to be high level elevated to be able to transmit the signal with a good direct path. And as a result of it, you will notice that they are located on top of the hills that are prone to ice, heavy snow can affect them, and bushfires in Australia are one of the biggest challenges that most of the basically telecommunication network owners are dealing with. So this is an example and a sort of sample of a microwave tower. And this photo is actually from one of TasNetworks sites. It's fairly old. It's from 2009. Many of these has changed, but it was a clear sunny sky, so I chose this photo over many of the recent ones with not very nice skies at the background. But the antennas are still sort of the similar type antennas. And I found another photo of the site that was basically, we experienced a bit of a bushfire, and you can see there were two huts sitting next to the tower, which basically all the comms equipment and gear were inside of the hut. Lucky enough, this hut was empty, but you can see the hut was completely just out of the heat of the bushfire in the surrounding area, was completely destroyed. And as a result of it, these are the expenses and costs and risks that you're taking when you're building a microwave link. Last but not least is the infrared media, unguided media, and the best example of it is your remote controls basically at home are infrared. They're using the same sort of signal as the optical fiber cables, but instead of using the actual cable, because they're using the air as the media, then the length of it is not going to be very long distance. So it is really good for short distance and low bandwidth requirements, such as the remote control, but they are not really good for any other use. Another example of it, if you're my age, you will recall these phones structures that we used to sort of keep them together to send a bit of signal from one phone to another. They had this infrared section at the top of the phones, and with the slight movement, the connection would be lost, and then you had to start sending a megabit of data with infrared. Excellent. So now that we talked about all the different types of medias, I'm gonna start talking a little bit about the fiber optic cable and go more in depth of fiber optic cable and why it is so popular. So fiber optic cable basically is categorized into two different models. There is a single mode fiber optic cable versus the multi-mode fiber optic cable. Single mode fiber optic cable is made out of, or basically I would say all of these type of fiber optic cables, they are made, they have the outer diameter of 125 micrometer. And if I want to give you a bit of an understanding of how thick is 125 micrometer, your hair is ranging between 17 to 181 micrometer. So the outer diameter of fiber cable is, you can say it's really about a thick hair. That's all it is. It's just about the thick hair is the outer diameter of the cable. So the outer diameter cable is what I was explaining about, is the glass or a plastic with a low density, basically low. It has a low clarity, it's less purified. And then you have got the inner core with a higher density glass or plastic that can have different diameters, and the different diameter in the inner core will create basically different type of fiber optic cable. The one in the 62.5 micrometer used to be the first generation of multi-mode cables, or they called it OM1, and then the OM2, OM3, OM4, OM5 cables are different generations of multi-mode cables. I'm not going to go through all of them, but they're all in the 50 micrometer range. And then when you compare the multi-mode with single mode cable, you will notice that the single mode is only 9 micrometer, so it is even thinner than your hair. It's just the central core of the fiber optic cable. So what's the difference? What happens when you transmit signal in the single mode versus multi-mode? Well, in the multi-mode, because the inner core in a pipe is bigger, you can radiate signal in multiple directions, and the signal will basically, as I explained, bounce between inside of this big shield. It will bounce up and down, and it will go to transmit through. Versus the single mode, that is basically, it doesn't, it still bounces, but the bounces are so minor that we can really show it as a straight line, because it is such a thin pipe that the light doesn't really bounce between it, and it goes more of a straight line inside of the cable. If you want to compare them together, basically the multi-mode, given the bigger size of the pipe and the way that the light is transmitted, the light transmitted in multi-mode, because the pipe is big, you can use a LED to transmit the signal. However, in the single mode, because your light needs to be concentrated into one point, you will use a laser instead of a LED. And as a result of that, you will have different attenuation between multi-mode and single mode fiber optic cable. So basically, if I want to compare the attenuation rate of a single mode versus a multi-mode fiber optic cable, for a frequency range of, the wavelength range of 1310 nanometers of wavelength, the attenuation rate for a single mode fiber cable is about 0.3 dB per kilometer, versus the attenuation rate in the similar range of wavelength for a multi-mode cable, which is about 1 dB. So it is 3 times bigger and more attenuation for a multi-mode cable versus single mode cable. And that the reason that makes it makes the multimode cable to be used only in short distances and not in long ranges. So before I go in more depth of multimode and single mode, the other thing that I need to mention is give you a bit of a refresh your memory from science in a school, that with the range of the wavelengths and how these 1310 or even that 850 that is mentioned here, where they sit. So basically the visible light wavelength is ranging between 380 to 740 nanometer. And the operating wavelengths in fiber optic cable is sitting in the infrared rays, which is basically past that visible light. So the light in the fiber optic cable is not visible, and it is very important and very difficult when you're working with fiber not to look into the center of it, because the light coming out of it can be quite dangerous, and it can cause blindness over a long time. So when we are working on the fiber, when we are making sure the fiber is cleaned and good to be used, we always have to make sure that we use glasses to basically filter and shield off those infrared rays, not to hit our eyes, because as I said, they can be quite dangerous. So I was saying that the single mode fiber cable can be used in the longer distances, and multimode is used in the shorter distances. And you might say, well, what's the point of using multimode at all? We would just use single mode in short distances as well. Well, it is always down to cost. And when you compare the single mode versus multimode, the single mode can be 5 times more expensive in terms of the transceiver cost. So not the cable cost necessarily, the actual equipment used, the laser that is used to transmit and receive data. Because as I said, the signal should be more concentrated to the center rather than being scattered. As a result of it, you would require a more expensive piece of equipment. So if you're connecting your equipment together and your equipment are within 100-meter range from each other, and you need to connect, provide 20 links between your, for example, your storage server to your web server, to your switches, to your routers, and there are 20 fiber connections required between them. The difference can be a difference between $2,000 investment or $10,000 investment. So it is quite substantial. And then if you expand your network, getting bigger and bigger, obviously you can do the math, it can get quite expensive. So as a result of it, there is a bit of a IT infrastructure within the site. They tend to use the multimode cables, or if it is a connectivity of even on the substations, for protection and control of them, because it is just going from the equipment going to a switch or to a sensor. Then you're not transmitting data in a long distance. Then by all means use multimode. But then when you're using the communication between two sites, if it is a 1 kilometer, 10 kilometer, 100 kilometers, thousands of kilometers, then single mode fiber optic is the solution. And because of the amazing distance you can achieve with the single mode fiber optic cable, basically some genius people in years and years ago, they started using it, installing it under the oceans and seas and on the ground, and basically created the internet. So there is this website that I don't know if you have ever looked at it, but I really think it is amazing. I would definitely recommend you have a look at it. Obviously, neither TasNetworks nor myself are not responsible for the quality of data or the correctness of them, but I do recommend to have a look at this website. It basically, what it does, it shows you all the fiber optic cables installed so far under the oceans and seas, connecting continents together. As you can see, it's a lot of them. It is quite interesting that you can click on every of them on the website, and it will give you detail of what type of cable it is, what's the distance of it, what are the sort of destinations. It is quite interesting. You can look into it. Some of the islands, tiny islands in the middle of the North Pacific Ocean, or the Atlantic, that you ever think of why ever anyone would put equipment in there, or it is so important for a country, then they fight over it. They have got wars over it to take ownership of why they're important. Well, this is one of the reasons that they are why they're one of the many reasons, I'm sure, that why they're important, because there are hubs. For example, in this location, there are hubs of connectivity of many countries together. I took a snapshot of Australia and how it looks like on the map as well, and you can see there is a fair bit of connection going from Australia. There is a sort of the big link going from here to Oman, and then a lot of links to Singapore, connecting east and west together, and then multiple links from Sydney going to different locations. There are 3 links connecting Australia to Tasmania. 3 cables. One of them is the Bastlink cable on the one on the right, and then the 2 on the left basically are the cables installed and owned by Telstra. So basically all the internet connection of Tasmania is provided by these 3 cables. So again, this is the website. I would definitely recommend you to go and have a look at it. It is really interesting. So the single mode and fiber mode cables, I put a photo of them there because there is a good chance that if you go to sites, and not necessarily a telecommunications site, but even a power station, you may, or substation, you will see many of these cables connected. And I thought maybe it's a good idea just to give you an idea of what type of cable it is. So next time if you see them, you know what cable you're dealing with. So generally speaking, they have got different, obviously, ports at the end of it. So there are different types of connectors at the end of the cable. I'm not going to talk about those because it's another 10-minute presentation on that. But basically, there are orange cables. There are multi-mode OM1, OM2, the thicker one, thicker core. And then the aqua cable, it is a multi-mode OM3, OM4. There is a green one, rarely see it, but it is OM5, it's a new technology. And then the single mode fiber optic cable, which is the yellow patch leads. So these are all the, basically call them patch leads. They're used inside the sites to connect the, connect the termination panels into your pieces of equipment. However, on the outside plant, on the streets, on top of the poles, the story is a bit different. The fiber doesn't look like that. It looks a bit different. So many of the pits that you may have seen on the ground, on the pavements, as you walk in the CBD, you will see there are different telecommunication owners. For example, in TasNetworks, we have got TasNetworks pits and infrastructure. So this is actually a photo of one of our pits. I opened the pit to take a photo of it. You'll be able to see there is a underground fiber optic cable, which is a basically blue cable. And it is normally 99% of the time is the blue cable. You will see it as the underground cable coming to the pits. What happens really inside of the pits is either used for changing the direction or having access to the cable, or also they use it to joint the cable to each other. So they can join the cables to each other because of various reasons. Either the length of the cable wasn't enough, they wanted to extend it, so they joined it together, but also they want to branch the cable into multiple locations. So imagine you have got a fiber optic cable coming from the north of the city, and you have got a fiber cable coming from the east of the city. The way to join them together, you use one of these, and then once you join them, you have got a full connection from north to the east of the city. So the way that these things, how they look inside, basically is created a sort of consist of a number of trays, and in each of these trays, they basically fiber cables come inside, and then they strip the cable, and they end up with these tiny might use my spotter. They use these tiny strands of cable, if you remember, 125 micrometer thick hair, which is the outer cladding of it. And again, this one has a shield on top of it to color code it as well, so a little bit thicker. And they basically fuse and splice every single of these fibers together. The way they connect them together, again, I didn't include it here, but they basically use an arch, electric arc, so it will create an instant heat between two pieces of glass, and they fuse them together to fuse every single glass into each other. Obviously, it's a very time-consuming job. And as a result of it, the deployment of fiber can be a bit expensive compared to other structures. The other type of the fiber optic cable, you may have seen it, or perhaps after this presentation, if you have never seen it, you will notice it when you go out on the street, is the lower than on the HV LV towers, poles. You will see there is a cable installed, a black cable installed. That is a fiber optic cable. It can be owned by many different network owners. There could be NBN, Telstra, or in this case, this one is actually TasNetworks owned ADSS cable, as they call it. And I took a photo of it again with the splice enclosure. This time it is mounted on the tower. So then the cable coming in and out, it is spliced here. And in this scenario, it is actually branched out to an underground cable. So they spliced it and they took a branch out to deliver a service to a certain customer in the premises. They use one of these junk boxes or splice enclosures. And the last type of the single mode fiber optic cables, that is basically not the last type, because there are multiple types. There's a submarine type as well, but the last type that is used in most of the power transmission distribution companies or any telecommunication network companies is the OPGW cable. Well, the OPGW cable is really used only on the transmission tower, so it is the ownership of it, generally speaking, is the ownership of it with the transmission business. So the way that it is used is the OPGW stands for optic ground wire, and what it is basically the earth wire that was used for earthing and to arrest the lightning. Is also they have used and put a strand of fiber or a few cores of fiber. Historically, it was when the technology wasn't evolved enough, it was only 12 fiber. These days, it is 144 cores of fiber inside of each OPGW cable, so they can maximize the use of technology and bandwidth and put more and use every single strand of it for communication. Going back to our communication slide that I explained before, as I said before, the full communication is not just we talked about the transmission media section of it. We talked about how air vibrates and goes through from the mouth to the ear. But we also explained there is a fair bit of protocols happening. There are lots of other functions happening here and here between the transmitter and receiver, the protocol and the noise that are affecting the fiber network, affecting the telecommunication network. Sorry. So now what we are going to do, we're going to talk about a little bit of those protocols to understand how these protocols are fitting basically together. So if you've heard of these names now, hopefully they're going to make a little bit more sense to you what they mean and how they fit in together. So a bit of a refresher. I'm pretty sure you all are familiar with the TCP IP model. You may not necessarily remember all the layer names, but you remember that there is a widely accepted TCP IP protocol model, which basically used as a foundation of telecommunication and IT networks. This is how we, on everyday basis, we use our different applications, obviously with different protocols. We're using different applications, our emails, web browser, Skype session, this session that we currently have, they're all using the same structure to transmit signal and deliver it from a transmitter to a receiver. So to explain each of these layers a little bit easier and better, I've used an type of analogy of sending a letter to a colleague. So imagine that you are writing 5 letters. You are writing 5 letters, and your intention is to send those letters to 5 different persons in TasNetworks. So you're writing a letter, and you're sending it, one of the letters to me, one of them to my colleague Daniel, and then Marco, and 2 other people. You're sending you're writing it, and you will label it as this one is for Farshad, this one is for Marco, this one is for Daniel. So once you wrote your letter, you put your content inside the letter, you will sign it, you put your fingerprint. If you're old class, you put a bit of a sealing on top of it to show that it is authenticated, it is definitely from you. And once on opening, there is no loss of data in here. Everything is in it. If there is anything attached into it, everything is packed into that. You have sealed it. Once you've done that, you're like, okay, I'm not going to send all of these 5 letters individually. I'm going to put them in a box, and I will label that box to go to TasNetworks. It is located at 127 Mariah Street, Laney Valley, 7W8, Tasmania. Now, once you've done that, as I said, you address the box. So you put that address on the box, and you put it in the mailbox. You give it to the mailbox, the mailman picks it up, go to the post office, follows a few routes, and ready to be received by TasNetworks. So we looked at it from the top to bottom. So you are the transmitter going to the mailbox. Now let's go have a look at it, what it happens when it comes to TasNetworks. So the mailman delivers it to TasNetworks with the address that it says it is going to TasNetworks, 127 Mariah Street, the address. It gets to the security desk in TasNetworks. The security desk says, okay, this is the box for TasNetworks. I'm going to open the box. What is inside the box? There are 5 letters. 5 letters individually mentioned. One of them coming to Farshad, the other one going to Daniel, the other one going to Marco. So the security person delivers each of them to the individual person that was labeled. I received my own letter. I see, oh, it is perfectly sealed, signed. I know I'm not losing any piece of information. The information is not corrupted. Nothing has changed in the information. Is it authenticated? And then when I'm confident that the information is correct, I will open the letter and I will start reading the data. So the top 2 layer, what I've tried to explain is the layers that are the user ends, the application and transport layers of the TCP/IP model. They are basically on the user side, on the still obviously application side, there are certain protocols that authenticate, make sure that the data is not lost, the data is completely correct there, and how the data is presented to the user, to the end user. But also there are the 3 bottom layers, the network, data link, and physical layer, and these are the network entire part of the layer, the network. So these are the ones that are responsible for transmitting the signal, for delivering the signal, making sure the signal is going from A to B. So let's have a look at each of these layers, and some of the technologies you may have heard how they fit within these layers and how they work within these layers. So in the physical layer, the bottom of the layer was the transmission media that we talked about. It was the fiber optic cable, microwave, twisted copper cables. They're foundation and basics of transmitting the signal. Now, when you're transmitting a signal, let's say you have got a fiber optic cable, you have installed it across the Atlantic. Every single strand of it, very expensive. It was a multi-million-dollar project, and you have got a limited number of cores. Obviously, you want to maximize the use of every single core. You don't want to use it for basics. You want to use it as much as you can. So what you do, you use WDM technologies. So what is the WDM? Basically, is the wave division multiplexing. If you recall, I was showing you the attenuation rate for in different wavelengths for optic communication, basically. And I was telling you in a single mode fiber optic cable, we were using a 1310 and 1550 for attenuation. And the reason for that choosing those, and I was showing those, was that the attenuation obviously changes over different wavelengths. It has different sort of characteristics in different wavelengths. And in 1310 and 1550 is relatively low. So what they've done, they have chosen some of these bandwidths to divide the data, or basically transmit the data into different wavelengths, into different wavelengths in different channels. They have sent the signal. So in one strand of fiber, instead of just sending one signal, they're sending 10 signals at the same time, for example. There are two different types of wave division multiplexing. There is the CWDM, which is basically coarse division multiplexing. It is across the full band. It is coarsely, the channels are separated from each other. They use to transmit the signal. There's also the DWDM, or basically dense wave division multiplexing. They use the C-band and L-band, which has one of the lowest attenuation, and they very densely set the channels right next to each other, and it can go up to 80 channels in a DWDM. With a similar network to the DWDM network and right modulation, we have had the transmission rate over fiber optic cable of 179 terabits per second over 2 kilometers of fiber optic cable. So you can achieve a lot of communication. And to give you a bit of a scale, it's only a few gigs gig per second, only I think 10 gig per second for a 8K uncompressed sort of data to stream. So having that link, you can basically stream any all the Netflix movie at the same time in your house. After the DWDM, basically DWDM is a bit of a relatively new compared to SDH and PDH. We have got the SDH and PDH. So SDH and PDH was relatively older compared to WDM's technology. And what they were doing, they were using time multiplexing to send the signal. So instead of sending all the signal at the same time, they will allocate a frame of time for a signal to send let's say 100 microseconds for each frame. It's 125 microseconds for each frame to send a bit of signal from different sources, and then it will switch again, goes from start 1, 2, 3, 4, 5, again 1, 2, 3, 4, 5. So it doesn't send all of them at the same time. As a result, you don't maximize your bandwidth compared to the WDM, but still it was better than just using the fiber just for transmitting one signal. The SDH is basically a synchronized transmission. So all of your equipment are using a GPS clock. So all of them are synced together. So the frame 1, when it happens at 8 o'clock 00001, the other piece of equipment, it knows that it was transmitted at exact that time. So they match their clocks together. Versus the PDH, which is almost synchronized. It's not using GPS clocks, they're using internal clocks. And because of that, they were not amazingly great. They're still widely used, but they're compared to SDH is not, they had some defects. So PDH is no longer is used. They're moving toward SDH networking signals. These are all part of the physical signal. So all the WDM, SDH, and PDH, what you hear about, it is really still in the basics of the communication. They are smarter than the fiber optic cable, but they're not in the layer 2. What they really call them is the layer 1.5, because they're not as dumb as a fiber optic cable, but they're not as smart as the data link layer. So they're in a 1.5 area setting. After that, you have got the Ethernet. I'm not going to get into too much detail of the Ethernet, but basically it is used for the basic concept of it. It is used for a connection in your office, for example, to connect your computer and send a signal to your colleague sitting next to you, and also connecting your office, your head office, to another office, or you're connecting your office to the internet. Ethernet is used in a combination of switches and routers and network gear to communicate data. So there are certain switches and routers used as a gateway to connect the data, connect your internal network, internet, or your organization to the internet. But to maximize, again, the speed of the transmission, to maximize the transmission rate, what they have done, they advanced the technology and they moved a little bit. One type of Ethernet that was using the MAC addresses. So every piece of Ethernet equipment you have got, your laptop, your router, that are having an Ethernet port, they are having a hard-coded MAC address, MAC ID. That is the ID that identifies globally your laptop and separates it from any other laptop. To maximize the switching and routing within the network, to send the package very quickly. Remember the analogy of the MAC address was sort of going to sending it to TasNetworks sort of thing, and going to Farshad and Marco and Daniel, to even make it faster. Instead of relying on, okay, TasNetworks as that is 127 Mariah Street, they came up with the MPLS network, which basically is tagging. And it says, instead of focusing on the addresses 127 Mariah Street, let's focus on the postcode, which is 7008 for now. We'll just send it to 7008, then we'll think about how to transport it from there. So there is an MPLS. It doesn't look into what is happening inside. It just looks into the bigger region. It just looks into the tags. It just focuses on the tags, sending the tags instead of focusing into the full detail of it. So it makes the switching and routing much faster. And then on the top of it is the network layer, is the IP, which is basically those names on each of the letters that we were talking about, which is, that is to Farshad, this is to Daniel, this is to Marco. The Ethernet and IP network is basically, they are a combination of data link and network link. They're very close, working closely to each other. It is hard to separate them from each other. But the MPLS network is sharing a characteristics of a bit of both, and as a result of it, similar to these ones that they were calling it layer 1.5, they call MPLS a layer 2.5. It is not fully Ethernet, it's not fully IP, it is somewhere in between. It is, as I said, using the sort of fast switching and routing to increase your transmission rate. Excellent. Now let's have a quick look at some of the network modeling examples, some of the real examples, how all of the things that we talked today are connected to each other, how they work together. Imagine you have got the TasNetworks example, Department of Education. They have got a school called a school, let's call it school X. They want to connect a school X to a Department of Education a storage server in the data center. And they want the school Y having access to the same information in the data center, and also they want these two schools having access to the information from each other. So what TasNetworks does, we go and install a piece of equipment in Department of Education's premises, connected to our fiber optic network, the one that I explained before, and we take it all the way to our data center. In our data center, where we have provided a rack, location to Department of Education to install their equipment. First, we shape the bandwidth, we provide them the bandwidth that they're willing to pay for it, and we pass on the access, we pass on the bandwidth with the pipe into their equipment. So then they can share the data from school X in a certain bandwidth provided by TasNetworks to school Y in a certain bandwidth that is again provided by TasNetworks. Now, if those schools are widely separated in terms of location and they're far away from each other, again, TasNetworks is gonna, or any other network, I'm just giving the TasNetwork example, any network, what they will do, they will provide and they will create a connectivity between their smaller communication facilities they have got. We call them points of presence. So let's say school A is connected to a point of presence, school B is connected to a point of presence. These are in the north, and then school C is connected to a data center in the south. All the information, all the racks, everything is in the south. TasNetwork has a big pipe of bandwidth between this pipe in the north and this data center in the south, and basically create a full network from C to A and B. So all of these schools are fully connected to each other, even though they're far, far away from each other. And they don't even need to have access to the internet. They are just relying on TasNetwork cloud system to connect to each other without needing to have access to the internet. Excuse me. So I'm aware of the time as well. I'm just gonna quickly go through the next couple of slides, which is almost the end of the presentation. Gonna briefly talk about data centers, and I was sort of saying that they're holding all of their information in a data center, but I'm just gonna explain what is a data center. So a data center is a purposely built facility to store and hold all the IT equipment infrastructure. So all the switches, routers, all of the things that they talked about, all of that DWDM network gear, they're all held within communication facilities and data centers. So a data center, obviously, because of the scale of it, for example, in TasNetworks, because of the scale of the data center we had and the use of it we ended up leasing a lot of our space to a government and non-government enterprises. So a data center needs to tick a few boxes, meet a few requirements to be called a data center. The most important one, or one of the most important ones, is the security of the data center. All the infrastructure, that IT equipment that are sitting in that room, in that building, they are prone to risk of cybersecurity, loss of data, or malicious acts. Someone just basically affecting data by destroying the equipment. So there is a certain level of security need to be maintained for a data center to make sure that only authorized people are able to access into the data center and into those equipment. After that, there is all the IT equipment require reliable power connection. So in the data center, normally they have, what we have in our data centers is more than one feeder providing power into the data center. So if one feeder loses power, there is still another feeder providing power. If both of your power feeders lose power, we still have generators to generate power. Even with the generators, we have got redundancy in the generator. So if one of them is under maintenance and you lose both of your feeders, you still have one generator to provide power. However, the issue is that when you have got a generator in a data center, it normally takes about a minute for the generator to kick in and supply power. And that 1 minute is not something that any IT engineer can accept, because even in that 1 minute, they could cause a lot of damage to the data, loss of data for many of the networks. So what we do, we put UPSs in between. So an IT equipment, normally they can handle when they lose power, they can still function 20 milliseconds after they lost the power. So As long as you provide power in the first 20 milliseconds, no interruption, it's all good. So we have got UPS systems, which is basically battery backups, and they kick in the moment they lose power. The main feeder is out of power, provide power to the equipment, so the equipment don't feel any interruption. And then after a minute, once the generator is fully functional and is providing power, then the UPS will shut down and then it will switch on into the generator. And obviously, by using all of that power into the IT equipment, a certain level of heat will be generated by your equipment. What will happen? When the heat increases, same as your laptop, if there is no fan on your laptop, or it will basically burn and it will completely cook. The CPU in your computer will completely cook and it won't be usable anymore. So what they need to do in the data center, there is a certain level of humidity and temperature that need to be controlled. So you can't have too high or too low humidity because that can affect your equipment, the longest lifespan of your equipment, and also the temperature need to be maintained within 23 to 26 degrees. So if you go beyond or less than that sort of temperature, then again, if you go less, it is not very cost effective. If you go higher than 26, 27 degrees, it is not gonna really be helpful and healthy for the health of your equipment, your IT equipment. So it is very important, many of the communication facilities and data centers to have and sort of they tick those boxes and make sure that they are in a safe and reliable, basically, environment. The last thing on the sort of in the data centers is the cleanliness of the data center is quite important. So basically, because of these cooling systems and they're pushing a fairly high airflow through the equipment, dust can go through the equipment, and dust sitting on your equipment can cause a short circuit in your basically equipment. So you need to make sure that your data centers are crystal clear and there is no dust entering into your data center. On that note, that will be the end of my presentation. Sorry it took a bit long. I expected it would be shorter, but somehow I managed to talk about an hour.
Thanks very much, Farshad. I mean, it was an extremely interesting topic, mate, and I guess good to start with that basics approach, but then start to peel back some of the shroud behind the different medium, the telecommunications medium and telecommunications approaches. So I definitely found it as a probably a bit more of a through and through power engineer, found it extremely informative. We do have a few questions that have come in, so just a quick reminder, with the presentation being fairly full of information packed to the hour and a half, we probably got time for 2 or 3 questions, which we've got at the moment. But if you do have any further questions at the end of this presentation, I'll put Farshad's email address up. If you are interested in getting in touch with him or asking, a couple of questions maybe that don't get answered, I think Farshad said that's okay to contact him with the caveat that he's busy, he may not respond immediately. So first question that we have, Farshad, is one from Dai Jirol, is one relating to so I'll read it verbatim. So I understand that single mode is more capable of long distance transmission than multi-mode, but it is more expensive. For OPGW in overhead transmission lines, do you also use single mode optical fiber, especially for long distance transmission lines, which I think is one that you answered, but that's the first part of the question. So
Yep. So yeah, you're right. So the price of the fiber, I need to say that the price of the fiber is not very different between multiple and single mode. It is the transceiver equipment that is used that basically makes up the majority of the costs. So yes, definitely it is a single mode fiber optic cable on OPGW. In terms of the given that the fiber optic cable is basically it's not affected by electromagnetic radiation. That's basically provides an advantage and makes it possible to put the fiber inside of the cable because electromagnetic radiation doesn't affect it. However, in a very high rate, basically transmission rates, when they use it in DWDM, it can affect the polarity. So every time that you have a lighting, it can actually change the polarity of the transmission receiving of the signals, of the light signals in OPGW cable. And because of that, there are equipments on both ends of it for DWDM's networking to constantly monitor the polarity. And if the polarity swaps, they will swap their polarity on the equipment. So then the network wouldn't be affected and wouldn't see the change.
So that you might have even touched in then, if I've understood that answer. So the second part to that question was, is the lightning resistance the same for single mode and multi-mode?
Yeah, so as I said, the lightning normally shouldn't affect it, and I don't, because they don't use multi-mode on outside plant. I don't know how it works on the lightning, to be honest, because I don't think there are many research done on it, or they were used on in the networks actually. There might be just papers on it, but not actually used widely on networks. But in the single mode area, I know that yes, it is widely used for DWDM, and it doesn't really affect in the low transmission rates, but when it goes beyond a certain transmission rate, then yes, it will be sort of important to consider those in your equipment to make sure the polarity wouldn't change and those sort of things.
Okay, thanks very much for that, mate. So another quick question. This is actually one from me, but you with technologies, or I guess capabilities like OPGW. I mean, historically we used power line carrier communications, particularly for protection functions. Do you see power line carrier communications being used much for new substations or new sites, or is it something that's sort of being phased out gradually in favor of fiber?
Probably this is one of the answers that a member of the protection control team would be more better off to you to answer to it. But certainly, yes, they still use it. Each of these technologies are still useful in different areas, and especially when you are looking into different costs. There are in shorter spans, and where it is possible, it is better to go with the cheaper technology. So yes, certainly we can still see them that they are used, but obviously, yeah, the OPGW cable, as they're even the technology in the past 10 years is sort of evolving and improving. Previously, as I said, it was 12 core of fiber cable. Now it is 144 core of cable. So there is a possibility of completely moving to the favor of the fiber. Yep.
Yeah, no, thank you. That answers the question. And we do have one last one, which I think is, or we'll have time for, from Phil, thanking you for the presentation, but also asking, so in recent webinars and texts, CIGRE study groups B3 and B5 seem to be providing more information on fully digital substations and their role in the future. Would a shift towards this type of installation have an impact on how TasNetworks manage the renewal and maintenance of their fibre network?
Look, yes and no. I say yes because if a substation is only connected to a radio link and the radio link is not able to provide enough bandwidth, so what's going to happen is that we have to upgrade our radio link. It might not still be viable. It may never be viable to install a fiber optic cable to that substation because of the area that is located, underground rocks and those sort of things might be very expensive. So all you need to do is really upgrade your network to be able to cope with the bandwidth that is required. But again, I really doubt the bandwidth will go beyond what we already have in any of our substations. Our technology, what we're trying to do in TasNetworks is that at the moment the lifespan, we are almost the end of the lifespan of our equipment. We actually upgraded to cope for the technology of the next lifespan of whatever 10, 20, 30 years of it. It is not going to really affect us in long term of saying that we are not coping with the technology. So what we are doing is we're constantly changing our technology to make sure that we are basically ahead of the technology of substations and the requirements for SCADA and all of those protections and controls.
Thank you very much, mate. I think that answers the question. And with that, mate, we may call it there because we're a couple of minutes over, but I just wanted to finish by again saying thank you very much for your time. It was an extremely informative presentation. Again, I think took us from the very, very basics of the medium and how it works right through to different protocols. So I think it was a very good overview. And maybe we have to get you back for another one in 2021, looking at the more detailed aspects, which is where I'll probably tap out in terms of understanding. But thank you very much, mate. Really do appreciate your time.
And yeah, no, my pleasure. Hopefully it was helpful for everyone. And yeah, thanks for your time.